Much like a three-dimensional box, we do have degeneracy, which is having different quantum numbers but the same energy. And if we were to look at the simplest possible case and realize that we're talking about wave functions, we can talk about the probability now of finding an electron between, say, r and dr. And what we can do is let's just take a look at the simplest possible case and say that there's no orbital angular momentum. Then the probability is going to peak right here, which is going to be what we would call the 1s state, and that's going to occur exactly where we would expect it to be, 5.29 times 10 to the negative 11th meters, which is the Bohr radius. Now, if it had more energy, then we would say n is equal to 2. It's going to peak right over there. We would call that the 2s. And then right over here, we're going to have n is equal to 3 and n is equal to 4. One thing to kind of keep in mind is when we're looking at the 2s and 3s and 4s, that the radii are going to occur just where we would expect them to based on the Bohr radius, which is that value for a that I gave you right up there. Once we start to give this atom some orbital angular momentum, we still will have degeneracy, and L is equal to 1 in a spectroscopic notation is actually going to give us the p states, and then we could have the 2p, 3p, and 4p, and these guys right here are not going to be spherically symmetrical like it will right up here. One thing to kind of keep in mind is that as we start increasing values for L, then we are also increasing our range of m sub L's, and we're going to have more degeneracy. Now this is starting to look a whole lot like some chemistry right over here, and you can kind of see that chemists like to write things with spectroscopic notation. And what's going on right here is the value for n is going to determine the electron shell, and the chemist would say that n is equal to 1 is the k shell, n is equal to 2 is the L shell, the m shell, n equal to 3, n, and n would be the fourth shell. And then L is going to determine the state, where L is equal to 0 is going to be what we call the S state. L is equal to 1, we're going to call that the P state. L is equal to 2, we're going to call that the D state. L is equal to 3, we're going to call that the F state. L is equal to 4, we're going to call that the G state, and so on and so forth. Something to kind of keep in mind as we're increasing our value for n, we're increasing our value for L, and more importantly, when we increase our value for L, then we increase our values for m sub L, and we get more degeneracy. One thing to kind of keep in mind about these probability distributions is that they are, three-dimensional, and what I mean by that, if we were to look at the zero angular momentum case, L is equal to 0, that we kind of have this shell that's going to be the n is equal to 1, and then we're going to have this guy right over here, which is going to look kind of more like a fuzzy donut, and that would be n is equal to 2, then n is equal to 3, and so on and so forth. And we're having these shells that are larger and larger and larger and larger as we get more and more and more energy. We do have regions where it's very, very, very unlikely that we will find an electron, and we have regions where it's fairly likely that we'll find an electron. Note that this does not mean that we know exactly where the electron is, and we still have the Heisenberg uncertainty principle that says, hey, if we know where the electron is, then we can't know how fast it must be going. So if we knew exactly where it was, we wouldn't know how fast it was going. So the Heisenberg uncertainty principle does still apply. Once we start talking about L is equal to 1, the P states, or L is equal to 2, the D states, then we go from having nice pretty shells like we had right over here to kind of some more funky looking patterns. They tend to usually be symmetrical, and that would be the 2p state with plus and minus 1. You just kind of see the plus and the minus. And then we have these guys right over here. Okay, now I want to talk about something called the Zeeman effect. And what the Zeeman effect really is if we were to expect to see a spectral line coming off of an atom, say at some frequency, and it might look like this, it turns out that if we turn on a magnetic field, that we're actually going to see not one spectral line, but maybe 3 spectral lines. The spectral line we would expect to see previously, so that's going to be this guy right over here, but then 2 on the side, or maybe 2 on each side. So what's up with that? If you recall back in chapter 27, if we had a loop that was carrying some current in this direction right over there, we talked about something that was called the magnetic dipole moment, which said that this thing is actually going to act kind of like a magnet. There's a magnetic field up here, maybe it's the north, there's a magnetic field down here, and maybe it's the south. So really this thing is just going to act kind of like a bar magnet, and that is definitely a dipole. And we said, hey, if we put this thing in a magnetic field, there's going to be some interaction energy, and that's actually going to be the dot product of this dipole moment and the magnetic field. Now if you just kind of think for a second about the Bohr model of the atom, where we had a positively charged nucleus and an electron just kind of whizzing around it just like that, that looks an awful lot like this guy right up here. It looks like a wire that's carrying some current. And so we can actually define some interaction energy in the same exact way. Now this guy right here is related to kind of the angular momentum L of this electron as it whizzes around. If for a second we were to put a B field that was just in the z direction, so if we were to put a B field just in the positive z direction, then we can define the interaction energy kind of like this. Now what this interaction energy is going to do is that this is going to shift the energy level ever so slightly. So we might have an energy level that was corresponding to this frequency right over here. We're going to now shift it up and down by a teeny tiny little amount, and that's going to give us these two little sideband frequencies right over here. Now you could actually even say that this U is going to kind of go like L. They're both related to the electron's mass and charge and mass, and so we could write the Z component of this dipole moment as such. And since this guy right over there is related to the quantum numbers m sub L, which if you remember for a second, m sub L is going to be equal to 0, plus or minus 1, plus or minus 2, all the way up to plus and minus L, we could even write it as such, where this little ratio right over here appears so frequently that we actually have a special name for it. It's called the Bohr magnetron, mu sub b. And for an electron, it's going to be this guy right over here in electron volts, or this guy right over here in joules. Definitely want to kind of have that guy jotted down. Now, the last thing I want to kind of finish off with a little bit is I don't want you to confuse these magnetic moments with electron spin. We'll talk about electron spin in a little bit. Here we're talking about the interaction energy simply because this electron is kind of whizzing around in a circle because it has some angular momentum, not because the electron is spinning. We'll see this guy again in a couple of slides. So let's take a look what the Zeeman effect looks like for just the hydrogen atom. We have our standard hydrogen atom with negative 13.6, n equal 2, n equal 3, and so on and so forth. And if we were just talking about the most simple case, if we had the case where L is equal to 0, then if you think about it, that kind of dictates the fact that m sub L must be equal to 0, because m sub L can only go up to L. In this case right over here, then we will have no shifts of the levels, and so we're just going to have our standard levels. And probably not surprising, if we had an electron that dropped down from this level down to that one, we're going to see just kind of one spectral line, one color. If we were to talk about one that was in the L is equal to 1 state, then we can now have m sub L is equal to plus or minus 1. And if we introduce a magnetic field, then we're going to have some splitting of the energy levels by some amount that is equal to U. And so we're going to have the standard spectral line that we're used to seeing. And then we're going to have another energy level here and another energy level here. And not surprisingly, when an electron drops down from those other two levels, then we're going to see two spectral lines on the side of that spectral line that we would see originally. Not surprisingly, if we move up to L is equal to 2, then m sub L is going to be plus or minus 2, and then we can have two spectral lines on each side of the original line rather than one. So what we can then kind of do is we can say, hey, our energy levels are going to be shifted by this little teeny tiny amount delta E, and if we had a and an energy level right here with no magnetic field. As we start to introduce some magnetic field, then we're going to start to have some splitting. The splitting is going to depend on the intensity of the magnetic field, as well as the quantum number L, which dictates m sub L. So if you were to consider this case L is equal to 2, we know that we're going to have our original line right over there, and then plus 1 and minus 1 for m sub L, and plus 2 and minus 2 for m sub L. And probably not surprisingly, as you increase the magnetic field, you're going to increase the splitting and increase the separation of the spectral lines. Now, one thing to keep in mind is not all transitions are allowed. We can only allow certain transitions. We definitely have to change L by 1 when we jump from, say, this state down to this state right over there, emitting a photon. So we have to change M or L by 1, and m sub L can only change by 0 or plus or minus 1. And this is dictated by the fact that photons actually carry some angular momentum, and angular momentum is always going to be conserved. So this diagram right over here kind of shows the allowable and forbidden transitions for the case where L is equal to, or going from L is equal to 2 down to L is equal to 1. You can kind of see we're going to have 5 splittings. And right down here, we're going from L is equal to 1, so we're going to have 2 splittings. And the dash ones are forbidden, the solid ones are allowed. Now, if that's actually not crazy enough, then there's an anomaly with the Zeeman effect, and it turns out that for certain atoms, we're not going to see the pattern that we would expect. For example, if you were to take zinc and not have a magnetic field, then you're going to see a line right over here. If you were to turn some magnetic field on, then you're going to see 2 lines on the side, just like we talked about earlier, so we're going to see the expected prediction. However, if we were to take a look at sodium, and we were to say, okay, well, I kind of predict a splitting where I'm going to see a line right here in red, and I'm going to see a line right here in red. Well, it turns out I actually see 2 lines on either side of that predicted line. And if I were to look at this guy right over here, I kind of would predict, one here, and one here, and one here, and that's actually not what we observe. And the same for this guy right over here. We kind of predict ones here, here, and here, but that's not what we actually see. So what's up with that? Well, it turns out that the electrons are spinning as well, as I alluded to on the earlier slide, and that's going to cause even more allowed energy states, so more splitting. So how did we realize that electrons were spinning? Actually comes out to a 1922 classic called the Stern-Gerlach experiment. Essentially, we had this oven that was firing off some electrons, and we passed these guys through a slit, and we passed that through a magnetic field, a very, very, very strong, non-uniform magnetic field. And actually what it did is it deflected the atoms very slightly upwards or very slightly downwards, depending on the orientation of their magnetic moment. And what they kind of realize is that electrons are either going to have what's called spin up. That's going to be a new quantum number called m sub s. Spin up would be a plus 1/2 spin, and spin down would be a quantum number negative 1/2. So now we have yet another quantum number to kind of play with. So what electron spin really is actually it's going to kind of be a vector. And I always like to think about it, if we had kind of the Earth rotating around the Sun, that's kind of like this magnetic moment, where we have the Sun right here, we have the Earth right there, and this guy is rotating right here. Now, if we were to realize that both the Sun and the Earth are also rotating by their own axis, that's what we would actually call electron spin. So the fact that we have some electron that's rotating around in this direction right over there, that's going to cause it to act like a magnet, and this would be a magnet that was in the spin up. If it was spinning around in this direction right over there, then it's going to be flipped around, so the north is up there and the south is down there, and that's going to be our spin down. So what we typically tend to do is we talk about the z component only, and what we find is the electron spin is also going to be a quantized value, quantized by the spin quantum number as well as our good old friend h bar. We can also talk about the z component of the magnetic moment due to spin, and that's just going to be this guy right over here, again a quantized value. So what this guy is going to do is it could take a spectral line just like that, and then it could split it into, let's just say 2 for the sake of our sanity. And what spin vectors are going to do is they're going to take these two predicted guys right over there, and they're going to split them even more. So while I might expect to find those two guys right there and right there, then the spin vectors is going to split it into the two green ones, and it would correspond to the plus and minus 1/2 over here, and the plus and minus 1/2 over there. Now, as we start talking about higher and higher and higher L, there can be some interaction between this spin component and this magnetic moment component. However, that starts to get kind of messy, so I'm not going to go there. So let's take a quick look at example 41.6 and the splitting of energy levels due to electron spin. If we were to consider an electron in the L equal 0 state in a magnetic field of 2 teslas, what interaction energy should we expect? What type of splitting should we see? Well, first of all, L is equal to 0 tells us that m sub L must be equal to 0, so we're not going to have any magnetic moment interference right over here. The only splitting we're going to see is going to be due to spin. So this guy right over there is going to boil down to this guy right here if we just take the magnetic field to be in the positive z direction. Actually, if we were to take it in the negative z direction, that would change that to be a positive. So this u sub z right over there is going to boil down to this guy right over here, and with just kind of plugging in the Bohr magnetron and all that other good stuff, we could see that we're going to have some energy levels splitting up by that many joules per Tesla. Kind of keep in mind that this negative sign right over here flips around this plus or minus, so rather than have a plus minus, now it's going to be a minus plus, and that's going to be important for whether we're in the higher or lower energy state. So in energy, or in electron volts or in joules, it's going to boil down to that guy right over there. And so the interaction energy is just going to be mu sub z multiplied by b, and so we're just going to take this guy right over here, plop it in right over here, or in electron volts 2 teslas, and you can kind of see multiply that by 2 teslas, and we're going to get splitting that's equal to this or this. Now, we do know that as we increase magnetic field, the splitting should also increase, and so due to spin and spin alone, if we had some energy level just like this and we were to turn on the magnetic field, then the spin up is going to split it in that direction, and the spin down is going to split it in this direction. Also, kind of keep in mind that if we were to turn our magnetic field around and we took z to be in the negative z direction, then the spin down would shift it in this direction and the spin up would shift it in that direction.